INRAE Research Director, but I am also CEO of the company Compliance Robotics, and I will try to explain a little bit what we try to transfer from research to application with the compliance robotics. And the idea is to create agile robotics for fragile world. So today the robots can be dangerous, in particular when you are in close collaboration with the robot, and this is due to the way they are conceived with rigid articulated parts. It's also not really well adapted for the manipulation of fragile objects, and it's maybe also not the best way to conceive robots for the future of the planet. So there is this challenge tried to be addressed by soft robotics, which is a new way of designing robots, and this research has been started maybe about 20 years ago, but it's much more active since the last 10 years. And the idea is to create robots that are adapted to fragile objects, less dangerous, and more resource efficient. In soft robotics, there are big challenges, which are modeling, design, and control, and this is the challenge that we faced in the team, in my INRAE team. So in terms of modeling, these last 10 years, we have developed a new approach, and in particular, to be able to use standard direct and inverse kinematic model of robots. So I hope you see the video. But so here you see a completely soft robots actuated with tendons, and there is a model on the left where it's an inverse problem. We can move the tip of the robot on the simulation, and the simulation finds how to pull on the cables so that it creates the deformation, the right deformation that put the robot where we want to place it. So this allows it to use soft robots as we are using rigid robots. In terms of design, we have also developed a full framework dedicated to deformable robots, where you can simulate the robot inside its environment. So you have the possibility to have a digital twin of your robot inside a possibly also deformable environment. And in terms of control, we also have been working on putting some sensors on the robot and try to close the loop. And in particular, we have been able to go to the point where we are able to do haptic feedback on a deformable robot. One of the big advantage of soft robot is that they can be controlled in position. So it's a little bit the same thing I showed before. Here is the very first robot we had in the team. The user can control the tip of the robot, and the simulations find out how to inverse the kinematics of the robot. But on the same robot, we have been able also to transform it as a force sensor. As the matter is deformable, as the robot is deformable, if you just measure some position of the robot and you have a good model, you can deduce from the deformation the force that is applied on the robot, meaning that you can really mix together rigid, so basically movement and force measurements. And the goal of that is that we can create robots in a complex environment, and in particular in cluttered environment. So, for instance, this is also an example of a robot. So it's the same trunk, also actuated by 8 cables here, and plus there is a motion of the base, and you have an obstacle. And the robot is asked to go from one point to the other, and there is obstacles, but the model can adapt to the obstacles and in particular find a strategy to continue to perform the same motion going from one point to another while there are some obstacles that appears. Meaning that here when you see when there is an obstacle, there is no obstacle avoidance, and but the obstacle is not dangerous for the robot, and the robot is not dangerous for the obstacle. Meaning that we can create really a new way of doing robot in a more complex environment. Anyway, so at the end, so here I showed you in a few minutes some research results that we had in the team. So it's a nice technology, but you may ask yourself how it can be useful for agricultural robotics. And I will focus on the use of this soft robot for pick and place application. So why there is a need of pick and place application is that today, when the manipulation of fruits, in particular for packaging, is mainly manual, and it's due to the fact that the fruits are very fragile, and it's difficult to. There is also a big diversity between the fruits and the vegetables, and it's environments that are quite complex, clustered, and one of the so basically the packaging is mainly manual again, but one of the difficulties is that at least in France, it's difficult to find people for doing such jobs, and in fact the population that is doing this job is also gaining in age. And there is a big question for the producer to be able to have sufficient people for doing this job. So there are solutions that have been popularized these last years. In particular, popular gripper solutions based on soft robotic technology, where you can use, for instance, vacuum in this case to grab a glass, showing that it can handle fragile objects, but also use like pressure-based grippers. So you can basically grasp an egg. It's secure, it's versatile, and it's delicate. And this has been already industrialized, in particular by the society Soft Robotics, the company Soft Robotics. But now there are also other company that is providing such a type of gripper, which are really adaptable and that are easy to industrialize because they can be put on the top of an existing robot, and they can be adapted to production. So here, for instance, you see the application of this gripper to the packaging of pears. But today at Compliance Robotics, we are thinking of doing it in another way, because one of the difficulty is still the proximity of the robot. So of course the gripper is adapted to the fruit, but still you saw on the previous video that the robot is moving fast, and being close to the robot is dangerous. And why it's dangerous? It's because to have a good efficiency, you need to go fast from the point where you pick to the point where you place. So in fact, this solution is mimicking the way human people would do the gesture, right? If I want to do that, I will do that way. But maybe we can create robots that do not mimic necessarily the movement of the human. And this is the idea we have in compliance robotics of making a robot, a hollow robot, where the object can go through the robot from one place to another, so that you have like local motion only here at one tip and local motion on the other tip, so that you don't have this problem of security with high cadence. It's easier to integrate, and it's probably less. There is probably less energy consumption and a durable conception of this robot. And the very first version of our approach designed in this 2D robot. Well, you see that the robot, in fact, is moving not very fast. There is no abrupt motion, but the productivity is very good. I mean, you see that the number of apples that are treated by minutes is very nice. But so I wanted to explain that this is what you see in the image is a simulation, and we have produced an exemplary of this robot on the right. One of the issue of this robot was that the apple were launched from a certain distance, and the producer doesn't want even if it's launched from a distance of a few centimeters, is still a problem for apples because they can be crashed or damages during the fact that it's dropped on the basket. So basically, we are now thinking of doing a new version of these robots, where we have separated the two approach. One approach is how to drive to create a hollow robot on the right, a completely hollow robot, and on the other side the conveyor. So for the hollow robot, in fact, we have found also other application of having a soft robot being completely hollow, for instance, for painting, etc. But it's not really for you. And we have produced this very first version of this hollow robot. And at the same time, we have worked on how to convey gently the apple, and we have developed this concept of a conveyor that would bring the apple till the end, so that you really avoid any fall of the apple. The apple is really protected, and we have in fact produced in reality this robot. So we have verified that we can really bring the apple to the tip of the robot carefully without any excessive pressure on the apple. So this is work that we continue to do. And now I will explain how we plan to go from research to the market. So today we have a technology that is up to date on simulation and control in particular, and we are at the level of deployment of this technology. And we have still research to be done on the hollow robot and the conveyor system inside the hollow robot. So today, the company is created, and we already provide some consultancy to companies that want to create a digital twin of the robot, because we have this simulation tool that is. So here it's an example of a catheter navigation that we do. So we do a simulation of a catheter robot for a company. This is not exactly this simulation, but I was so it was to show you a little bit. But for instance, if some of you.
Thank you very much, Christian. You don't know, but sometimes we had blank screen. But anyway, we have seen almost everything. Thank you very much for these nice presentations. Sorry, you cannot hear me? Can you hear me, Christian? Just 1 second. Can you see me? Not more. Just 1 second. There is some technical stuff. During the meanwhile, you can think about a question. I think that you have already many questions. And just the time we get Christian back. Christian, can you hear me? You don't. If you hear me, can you smile? Okay. He's still alive because his eyes is blinking. So, can you hear me?
Yes.
Ah, perfect. Thank you very much for this nice talk. Sorry for the technical issues, but it lets some time for the audience to have some questions. So if you hear me, do we have some question in the audience? Question. Okay, Farzan.
Bonjour, Farzan Ranjbaran, CEO List. Merci beaucoup pour la présentation. The question is, on the trunk with 8 cables, how many controlled degrees of freedom do you have?
So if there is 8 cables, you can control only 8 degrees of freedom. The problem is that the robot has more degrees of freedom than 8. So you have to deal to the fact that there is degrees of freedom that you cannot really control. So usually what we focus on is the control of the tip, and we adapt the control to be able to place the tip correctly. Does it answer the question?
So yes, it answers the question, and we have another question from Marco.
Oui, bonjour, monsieur. Good evening, good afternoon, better. I have a question concerning market development strategy. So the basic idea, as far as I understood, was to basically provide a general type of hardware while adapting case by case the software to the local issues. Is this the general idea? So basically, are you going to provide a general purpose robot, or perhaps in different sizes or dimensions, and then assist the client in adjusting the software characteristics, or what else?
So in fact we have different strategies depending on the topic. So for the simulation, the idea is that today there are some needs in providing deformation into a simulation of robots. So on this so the strategy we have is that our code is open source, and it's more helping people to develop so the code is SOFA, and we are helping people to use SOFA for their needs. The second thing is for the robot that today we sell is a robot for academia. So it's more to learn the basics of soft robotics to the students. So the robot has no direct use, but it's really the goal is to do some maybe small games, some board games with the robot, but not necessarily big application. But for the whole robot, the idea is that we are more developing a concept of a robot that can be adapted in size, which was your questions. So depending on the application, in fact we can rapidly recreate a robot of different size. And the advantage in that case of the software that we have is that the software can directly adapt to the new parameters of the robot. So if you change the size, if you change the material, in fact we base our models on FEM, on finite element method, so we are able to adapt to the dimension change of the robot. It's probably true that, for instance, we will not use the same robot for ananas or strawberry, for instance. So you need to adapt or do the same.
Thank you. So adaptable softwares for adaptable robots. There is another question of the first trunk. Yeah.
Hi, Christian. Thank you for the presentation. You have just shown some of the example of these soft robotics in the pick and place for the agriculture, but for the other application, like if we say harvesting is a big problem, like selective harvesting of fruits and vegetables. So what do you think, which kind of applications these kind of robots can be used? For example, there are different soft robotics or grippers which are being used for the selective harvesting of fruits, but there are not many like which could be used in vegetables. And what about the like robustness, like how much feasible is to use these kind of solutions in the open field environment with harsh vegetables? So I'd just like to know your opinion about that. Thank you.
It's a big question. It's a big question. In fact, there are multiple questions in the question. In fact, harvesting of fruits, for instance, can be assimilated to a pick and place task, right? You pick in the tree and you place in the basket. So it can be seen as a pick and place thing, and people are proposing this soft robot gripper. Maybe one of the issues with that is that they are often based on air pressure, so you need to provide air pressure to the tip of your robot, which is already, so it's already required to bring electricity on site, and it brings a new challenge. For pick and place, in that case, I think there is the same problem as we have in general, is that we mimic the gesture of the human. And in fact, the robot is doing, finding the fruit in the tree, picking, and then place. And it takes a long time. So I think in terms of productivity, it's not very, very good, in particular compared to the human performance. So for me, the idea is to leverage this with our solution and provide this hollow robot and being able to pick at one tip and place at the other tip. Now, for vegetable, your question was also for vegetable. So I think it's another problem because vegetables are often under the soil, and it's another issue. I don't have any direct solution for it. Probably there is more to do in terms of research.
Thank you for the answer. It's okay? Yes. Is there any other questions? We have time for one last question. No question? I have one, of course, Christian. You talk about the adaptability without hurting the object you took. Do you have also a pressure sensor in order to adapt the pressure, in order to grasp properly without damaging the object?
In fact, one of the advantages of soft robot is that you may not need a pressure sensor. You just maybe need a camera, a good camera, and some marker points. And if you, for instance, if you, as I was showing a little bit in my presentation, if you are able to measure the deformation of the robot and you have a good model of the robot, you can find the force that is applied on the robot. Because in fact, in nature, there is no force sensor. There is no pressure sensor. It's always a deformation sensor. That when we are able to measure the deformation, thanks to the modeling, we are able to find the force. And I think this is one of the good property of soft robots, is that we can have access to the force, the amount of pressure, more easily than what we can do with rigid robots.
Okay, and I imagine that there is also some special control law in order to adapt the shape.
Yeah, so the first thing is to add, so in terms of control law, there is a lot of challenge. The first challenge is to be able to do the inverse kinematics of the robot, because you may need to give a trajectory and to follow this trajectory. Then, when you have defined the trajectory, you need to probably close the loop. You have to measure and close the loop. One of the difficulties that the robots are
Okay, so thanks again, Christian. I hope you can hear the applause. And it's now time. You are welcome to stay with us if you want to hear the other presentation, of course. And now it's time to switch to the second presentation, which will be given by Axel Streit from the Wageningen University. Sorry for my bad. Okay. And I'm going to talk about robots for pruning, challenge and feasibility. So please, the floor is yours.
Good afternoon, everybody. I appreciate the opportunity to present some of my work today. My name is Axel, like you said, and so I'm a researcher at Wageningen University. And I'll be presenting some work that we did with the CEA in a project I did actually for my master's internship. It was a project of about 4 months where we did some rapid prototyping of a robot arm for pruning vines in winter. So I'll present to you some takeaways, some lessons, and the outlook for automating this task. So this is really a project where we had to do everything from scratch. So we developed this test bed, all of the software, integrate all the hardware. So we really learned a lot along the way. So quickly, a roadmap for the next 15 minutes. I'll quickly give some context, some motivation. Why is this a task that needs to be automated? We'll have a short look at current efforts towards automating this task. We'll discuss the approach that we took. We'll compare it to some other approaches, and then we'll look at what's still needed for in-field deployment, some challenges that we face. But in general, I hope to show you that this is an agricultural task that is feasible to automate with existing tools and technologies. So here we see a team of vineyard workers. They're braving the cold in order to prune the vines. And I can already hear some French people concerned that we're going to automate away the sacred art of pruning the vine. But the reality is this. I mean, if you talk to any farmer, they will tell you one of the biggest challenges that they have is finding enough people, seasonal workers, to do this task. There's a real shortage. For example, I believe in Gironde in 2018, 2019, only about half of the seasonal worker positions were filled, just to give you an idea. So this is creating an impetus for automating this task. Now, the thing is, we're not just talking about random cutting, okay? This is a task which the next year's harvest heavily relies upon being done correctly. If you incorrectly prune, you can really have a negative impact on your harvest for the next year. So it's important that this be done by skilled workers who have some experience. And then finally, it's quite a strenuous activity. You're bent over. So you can have some long-term health consequences if you're doing this too much. And so all of this kind of combines to create a need for automation in this task. Now, anybody who works in agricultural robotics will be able to relate to this problem, is dealing with variation. Okay, for example, in an automotive factory, you have the same exact part coming in at exactly the same place in the exact same orientation every time, right? So it's very easy for a robot to just do the same move over and over again. But in agriculture, as we all know, that is never the case. I mean, of course, between farms, you have variations in operational procedures, but even within a farm, within a field, every plant has its own structure, its own character. Right? And so that's really one of the biggest challenges that we deal with in agricultural robotics is being able to cover such a wide range of variation, right? And so here we see some examples of different pruning strategies which might be employed, but we're actually going to focus for the sake of this presentation on the one here, simple guillot. Okay, this is probably the simplest, but also one of the most common pruning strategies that you find. So this is quite a challenge. I mean, but there are a few reasons that this is actually one of the easier agricultural tasks to automate. So one is that we can make some assumptions. We can use our prior knowledge about how the plants are in the field, and we can use that to simplify our algorithms, right? So in general, for example, with this guillot system, the cane, the fruiting cane, is always trained along a wire. And so that tells us, you can basically assume that this branch is going to be in the same plane throughout the row. And that really simplifies machine vision, and path planning. There is also, in winter, as you guys are probably aware, no leaves. Okay, if you're trying to automate a task in a greenhouse or, for example, harvest, you're constantly bogged down because you have incomplete information. If you take an image, you don't know exactly where all of the fruits or all of the branches are, and that's a huge challenge. But the advantage is, in winter, we basically get the entire structure of the vine unoccluded. And that's kind of a dream scenario in machine vision. Right, and so this means that we can basically reliably detect all of the nodes, see exactly where the trunk is, and then make good decisions based on a good abstraction of the structure. So here we see two examples, one in research, one in commercial. This is actually a demo that I believe happened at FIRA 1 or 2 years ago, so you might have seen this live. Unfortunately, that robot is struggling pretty hard to find the branches to cut. And there are quite a lot of efforts. I mean, you have research efforts and commercial efforts. However, we'll notice there are no commercially available robots pruning vines. Right? People are trying, but there are still things that need refinement before it's ready for the field. We're going to talk a little bit about our approach now. Okay? So this is just a picture from our lab setup. So first we start from one raw image, an RGB-D image. So that's a regular image as well as a depth image. We don't use any LiDAR. From the image, we do some machine vision magic, and we can arrive at this abstraction of the vine. We'll go a little more in depth on how we do that. And then once we have a good abstraction of the vine structure, then we can apply very simple rules to decide where we need to cut. Okay, and now we're going to go a little bit more in depth. But first I need to explain a little bit just about the specific pruning strategy. So if you're not familiar, in simple Guyot, every year you have one fruiting cane, which you see here. Okay, and this is the cane which is basically going to carry the fruit of the next season. Every year, at the end of the season, that year's fruiting cane will be cut along with pretty much the rest of the branches, and you will leave one shoot which becomes the fruiting cane next year on the opposite side, okay? So they alternate sides. And so we choose this as our proof of concept because it's one of the simplest, but it's also one of the most common strategies. So basically what our system does is at first we have to identify where the fruiting cane is, where does it connect to the trunk, because you want that to be your first cut, right? This removes a lot of trouble. Once you take off the fruiting cane, you can remove basically all of this clutter. You can look again, and then you can easily find the other shoots that you need to prune. Here we go. So more specifically, kind of the first steps of our algorithm. So we start from our pure image, and the first thing we do is we run it through an object detector. And so this detector basically detects and classifies nodes on the plant, and it can classify them, for example, as the trunk in red, as the fruiting cane in blue, and as the shoots in green. Then what we do is we pass the highest confidence trunk node into basically a lightweight version of the segment anything model. So this is a foundational model which can give you really high quality segmentation. And this tells us exactly where the trunk begins and ends. This will become important later. But this is, the trunk segmentation is really critical, as I'm going to show in a second. All right, so on this side now, you can see kind of our complete abstraction without the connections. And then, but how do we get from here to here? As humans, we look at this, right? And we can kind of naturally see the structure. We can see that there's branches. We know more or less when we look at this here that this is a vine and what it looks like. But it's hard to translate that into an abstraction for a computer. So the first thing we have to do is we have to identify, right, which side is the fruiting cane on. Of course, here it's on this side. So we can use the trunk as an anchor, and we can connect the nearest node of the cane to the trunk, right? And this is really our region of interest for our first cut, is between this node and the contour of the trunk. And then we can start to use a nearest neighbors approach to connect node by node until we get this kind of tree-like structure here, which we can apply our rules on. And this all happens in 2D up to this point, also important to note. We are only working with the 2D image up to this point, and that's going to be a big advantage actually when it comes to speed. And then once we've built this full abstraction, we can start to apply our rules. Okay, so for example, we want to prune the fruiting cane first. So all you have to do actually is query your depth image for a depth at the pixel that you want to cut. So this is on a 2D image. And then that will output a 3D point where you can send the robot. And then this basically enables fully autonomous pruning actions based on a single viewpoint. Okay, and so here we'll see a little video demo. So you see, yeah, good job, guy. He should cut it. Oh yeah, there it goes. Right, and so this on-demand use of the 3D data is really what keeps the pipeline efficient. Okay, rather than continuously running this processing on a 3D point cloud, which can give you a very high quality structure of the vine, it's not strictly necessary, especially for the simpler pruning strategies. And this can really speed you up just using 2D segmentation as long as possible, and then querying for 3D data only when you need it. And this is enabled also by our prior knowledge of the vine structure, right? If we know more or less that you've got your fruiting canes in a plane, you can leverage that knowledge to simplify your algorithms. Okay, and here we have kind of a breakdown of how much we were able to execute cuts on the order of 10 seconds total, which is, yeah, at least on par with what a human can do. And it's really staying in 2D as long as possible that enables this. Okay, and these results were achieved on quite a standard GPU and actually using one of the lower quality RGB-D cameras. So I think with some better hardware, you can expect faster and more precise results. Okay, and now let's talk about some key enablers, some things that allowed us to achieve this stuff so quickly. Okay, one of the key things that helped us get here is this open source data set. So we got this from a company called 3D2Cut, and so basically we were able to build an object detection model very quickly without having to annotate ourselves thousands of images. Okay, and this is, again, if you work in agricultural robotics, you've heard this over and over, but we need to be open with our data because it really accelerates efforts, and you can learn really robust features from data sets like this, even if there's a bit of a gap between how your data looks and the source data looks. But of course, you can't get all the way there only with other people's data sets, right? You need a little bit of data from your own target domain, right? And so here you see, okay, this is an example of a vine which I annotated myself. And so here, basically what we're doing is we are complementing these large open source data sets with just a little bit of data from the conditions which we expect to encounter, right? So the specific lighting, the specific resolution of the camera, et cetera. And this is generally known as the generalization gap, okay? So what is the difference between the data in your training data versus the conditions which you're gonna see in the field? And this is a big thing. So the trade-off here is, do you want to make one model which can handle a wide range of conditions, or do you want to have one specialized model for every single vineyard, right? Generally, if you have a specific model for every vineyard, it might work better locally, but then that's also a lot of work to maintain hundreds and hundreds of vision models. Another key enabler, partnering with forward-thinking farms. Okay, we had a vineyard actually uproot and send us about 10 vines, which really allowed us to simulate the natural variation that you see in the field in our lab. Otherwise, you're stuck building fake plants, and that really is not representative of the types of conditions you're gonna see in the field, right? So my recommendation would be that when you're prototyping stuff like this is to partner with farms who are interested in making this sort of progress. Okay. As promising as all this is, of course, there's still several key steps which are non-trivial in order to get this technology out in the field. So of course, one, you need to attach this to a tractor or a rover which can move autonomously in the field. Totally non-trivial, that's to be seen. Two is extending it to new pruning strategies. Of course, here we focus on the simplest pruning strategy basically that exists. But there are many other pruning strategies, and we don't know if the assumptions that we make on this one pruning strategy will hold in all cases, right? So that is another thing, is developing new sets of rules. And then three, of course, is uncertainty awareness. So how do you know that a cut point proposal is good or not? How do you quantify that uncertainty? And then what do you do if your uncertainty is too high? Okay, so we have to address these areas. Speaking of uncertainty awareness, maybe you want to, oh, that's a shame. Can we play this video? Oh, that's a shame. All right. What I was hoping to show there was basically when for example, if you have a robot in the field and he's said, okay, well, I think we need to cut here, but our uncertainty is quite high. Something you can do is you can have an operator in the field, maybe with a tablet or so, quickly annotate that image for the robot. And that basically, one, it saves the vineyard from being destroyed by some confused robot, but it also can enable kind of a continuous learning cycle where your system is actually learning every time that it gets a high case of uncertainty. The thing is, when you have an uncertain image, generally those images are the most useful for retraining your model, right? Because they contain variation which is not covered yet in your training data set. And so you need some kind of a system to, yeah, okay, that's all right. We can, I'll live without the video. Oh, I don't even have my slides anymore. Okay.
Okay, no technician issue. Is it possible to have the presentation?
We have to restart the computer.
Okay.
The computer restarted. That's okay.
So you are stronger than the computer.
I got you. I will just give you the key takeaways then, okay? So number one is to keep your algorithms as simple as possible, right? This is in the interest of speed. If you want to deploy such a system in the field, it needs to at least be on par with about half the speed of a human worker, right? That's necessary for in-field deployment. Otherwise, no farmer is going to accept this. So keep using assumptions, using your prior knowledge of the plant structure to simplify your algorithms and your pipeline as much as possible. Of course, partnering with real farms is a huge accelerator. They know the practical problems. They can also provide you with specimens to help test in the lab. Hey, perfect. All right. Another thing, our systems need to be interpretable. Okay, you don't just want to rely on a black box neural network. When you have a neural network and it outputs a bad cut point, it's hard to know exactly what went wrong. Okay, but if you have basically a vision pipeline which remains unchanged, it's very easy to debug and see exactly where your problem is. And then of course, when in doubt, the robot should ask for help. Okay, a remote operator can really quickly clarify tricky cases that can save your vineyard, one, and it can enable continuous learning of the robot. Okay, I'm gonna try one more time to play that video. Oh, so here you actually see an example. Here I'm annotating an image live next to the robot, and what you'll see happens is the robot will just go and prune exactly where I put my points. Here you'll see. There you go, and now you can see our complete lab setup as well. But this is just a proof of concept for what you could have an operator with an iPad, for example. In cases of high uncertainty, he can quickly annotate the image, so that keeps the robot moving, and then the robot can learn from the human input. So this can be a really powerful tool as well. There you go. I'm glad we got to show that.
Okay, thank you very much. I think you can net the video during a question if you want. So thank you very much, despite technical issues.
That's all good. Thank you.
Unfortunately, we took a little bit late, so maybe if you have questions, we can ask questions.
You may find me at the bar out back.
So for a beer, he will answer your questions. Thank you very much again. And now we will welcome, not James Petri, but one of his students maybe. You will do the presentation for James? Yes, so it's your turn now. And you're going to talk about RGB-D camera for phenotyping. So I'm sorry I didn't get your name, so you have to introduce yourself.
Yeah, so my name is James Florin Petri, and this is...
Yeah, I'm Edward Jakunskas.
And we want to present you our work on proximal RGB-D-based phenotyping platform for cereal crops. So we are part of the AURA project, which stands for Automation in Robotics and Agriculture. We aim to find agricultural solutions through sustainable robotics. We are based in Maynooth in Ireland, and we have an on-site campus farm. If you're interested in collaboration, you can find our supervisor's email there and a quick QR code to our project website.
The aim of the project is to develop an automated short-range RGB image-based phenotyping platform that would reduce cost, reduce labor, and allow higher frequency imaging compared to the current gold standard, which is the Lycor LI600 fluorometer. There is a video there of one of the postdocs at the university taking manual Lycor measurements of each plant, along with the robot collecting images of the plants in the background.
So when we designed our platform, we chose the farm bots as they are gantry-based CNC-like farming robots that aim to automate most gardening tasks. It has exchangeable tools and originally came with a 6 by 3 by 0.5 meter work area, but we expanded it to 1.5 on the height axis to better suit the oat plants. The farm bots come with a Elixir-based operating system, which is not necessarily suitable for robotics research, so we designed our own ROS2 interface, which generates the F-codes for hardware communication. When we designed the imaging system, we wanted to image on both sides, so you can see the system there rotating. It had to get the multiple perspectives and have a simple design. So you can see we have a top camera, a 6-degree side camera, and a bottom camera getting images from all sides of the plant.
The first experiment we've run on the platform is to identify correlations between RGB-D images and the Lycor data. The first step is to simplify the image and to remove all the background noise. We actually used the depth anything model instead of the depth cameras because the depth images were lower resolution and weren't as good for segmenting the background. So using depth anything, we've just removed the background. We then used segment anything model 2 to segment the plant into different sections. And then we trained our own, or train a YOLO V11 model on our own data set to segment or to classify the leaves or the panicles out of the sand masks. The top leaf is an isolated based on the depth data, and we've extracted various RGB metrics like greenness or alpha chromaticity channel, and then ran correlations to see if we can find Lycor measurements from those. From the 8 Lycor metrics we tested, we found 4 basic correlations, those being leaf vapor pressure, which measures the vapor released from the leaf, as well as VPD, which is the previous measurement compared to the ambient water pressure. This one is very useful for just measuring the transpiration rate of the plant, as well as leaf H2O, which is just the absolute value of water released from the leaf. We also got correlations for leaf temperature. If it's too high, then it can cause heat stress, and if it's too low, then it would reduce metabolism.
So for future work, currently we have it all inside a greenhouse, and we want to transition it to an outdoor bed, which would better simulate the outdoor real-world agricultural conditions, including wind and other effects such as that, and taking steps towards implementing at a large-scale field setting.
We're also working on extracting more metrics through machine learning and 3D shape analysis, and be able to detect things like stomatal conductance from the Lycor, which we hope to do through machine learning. And we're also looking at agri-photovoltaics, where we will set up solar panels vertically and measure the effects of having the solar panels next to the plants compared to a test plot nearby that does not have solar panels, and just measure the efficiency of the field using both as opposed to just one.
Thank you.
Thank you. We have time for some questions. Is there any question in the audience? Question? While people are thinking about, I have one question. So you will switch from controlled conditions for phenotyping, and so you are in the building, and you now will switch to outside. So you will have maybe some problem in lightning conditions. How do you manage that?
We have a couple of ideas to go about that. One is to do the imaging at night with our own light, so that the lighting conditions are always the same. We could also use some computer vision techniques to normalize the light and look at the difference between color ranges as opposed to just the absolute values. So, yeah.
And is there any other issue with the point of view? Because in the building, you have always the same point of view, and you well control the position and orientation of the camera with respect to the plant. It will be, there is a risk that it's different inside, so do you have something to correct the position?
We're going to have IMUs and an RTK sensor on the Callan robot that we're building, so we'll be able to know exactly what angle it's looking down on the ground at, and account for that.
Okay, thank you. Any other questions? Everything was clear? Okay, so thank you again.
Thank you.
Thank you.
And now we switch to the next session, which comes from Wageningen. I'm trying to improve my pronunciation of Wageningen. About the evaluation of socioeconomic feasibility of agri-food robotics.
Thank you. Well, welcome everybody. My name is Jente Klein-Holkenborg. So I work for Wageningen University Research, and I'm sharing some insights about socio-economic feasibility of agri-food robotics. Find out. So I'm part of Wageningen Research and University. I work for Wageningen Research, which is basically a partnership of a research institute, of a university part, and actually a practical research institute. And we're all over the Netherlands, as you can see. We are in different sectors. So it's all about livestock research, research about marine research. Me, myself, I'm actually part of the plant research group. And we do economic research too. And then there is an agile group called Vision Robotics. And it's actually encapsulating all of these researches all together. So as long as it's robotics or vision-related tasks, you can be part of that group. And I want to share some insights about a project we are doing. And that project is called Next Gen High Tech. So it's a very big project, including the contributions of all partners. It's almost 1 billion euros. It's spanning over different sectors. So it's energy projects, it's composites, it's over the biomedical sector, semiconductors as well, and agri-food. So that's why we're involved. Focus really is on fast and precise robotics, and the goal is to finally further integrate automation and robotics into agri-food processes. So to give you an idea about the size of this project, these are all the partners involved. So it's partners from the industry, it's research institutes, and they're all working together to share their knowledge and to improve their products really. And the research institutes also offer testing and validation facilities, which is where we come in place. So my job in this project is actually to organize a very big part of all the testing and validation we in Wageningen do for all the different partners. So I went on and actually visited all of these companies in person, and we started a little brainstorm. And my question was, what do you want to validate? What can we do for you? And then they started writing things down on a big whiteboard, and they were saying, well, we need to be fast with our machine, and we need to be precise with our machine. So all different kinds of technical validations. And then after a while, we started thinking about how much can a robot actually cost? And do we need to comply to very specific rules, maybe? Super important. So actually, in the end, I could actually wrap all the validation needs of all the different companies in a very concise list. Besides technical validation, very important social economical aspects as well. Think about cost price, how autonomous must a robot be actually to be used by a farmer or end user. Do we actually reduce input, or do we reduce output like CO2 or nitrogen? So what we established actually, that there is much more beyond technical validation there. So a perfectly functioning system, technically, will never be used if a farmer doesn't actually trust the system or actually understand how it's used. So you can say, how do you call that? A technical solution must be intuitive and affordable, of course, and complying to specific rules, legislation. And think about legislation, because that's actually a constraint that's non-negotiable. So you really have to take care about, you have to think about legislation as well. So I was actually wrapping this in 4 different teams. So talk about practical usability, for example. It's all about ease of use. It's about system autonomy. So how autonomous must the robot be? And it must, for example, fit in a farmer's workflow. Then we are talking about trust confidence. Will users actually rely on a robot? Think about the milking robot. Can a farmer actually go to sleep while the milking robot is still doing its task in the barn? Sometimes the answer is no. We're also talking about financial impact, for example. So is it cost effective for a farmer? And finally, adoption behavior, really important. What does a farmer actually make use of the robot? So how do you get a farmer to embrace a new solution, basically? So what we did in Wageningen is actually we developed protocols for these teams to actually identify such questions, but also answer these questions. So you can actually indicate areas of attention, for example, but also strengths of a solution. Really, really important to make a solution be a success. So the protocols we made, or you can also call them tools. I call them essentials for performance and reliability of a development. So besides the technical validation, we actually made these tools. So one of them is called an ELSA validation. So it's all about ethical, legal, and social aspects of a solution. We also talked about user acceptance validation, business model validation, and economic viability, of course, all really important. So we make companies aware of these teams and actually validate all of these issues together with them to find out about their solution. So we're going to share some insights per specific tool. So first of them is actually the ELSA scan. So what is an ELSA scan? It's actually a structured assessment that identifies all the ethical, legal, and social aspects of a solution for example, a robot builder. And you ensure that your solution is also, besides technically functional, also an accepted innovation and actually a responsible innovation. And what does that actually mean? So for example, talking about ethical aspects, you have to ensure that innovations respect societal values, for example, addressing concerns like job displacement. Imagine developing an apple picker, and when it finally works, will all those workers actually be fired? Or should they maybe be trained and able to work with the robot as well? Also talking about data privacy, for example. So who owns the data? Is it the contractor who's driving with a tractor and a smart implement? Or is it actually the machine builder who built it? Or is it the owner of the land, like the farmer, for example? Or maybe even a third-party company who's acting as a data hub. So it's really important to identify these questions and answer them. For example, I was once working with a company and we were having a project about detecting fish on a fisher boat. And we were identifying species and size. And that was done using a conveyor with a camera on top. And we found out that at some point all the fishermen on board of the boat were not actually getting close to our system anymore because they didn't like being filmed. And after finding out, we could actually shield the camera, and that fixed the solution. And nobody thought about that because the camera was working just fine. Still very important. We're also talking about legal aspects here. So you have to verify compliance with certain legislation for your robot, for example. As I mentioned, those rules are non-negotiable, so you really have to take care of this. And a good example of that will be, for example, if you have an autonomous vehicle, finished driving on a field and you have to cross a road to get to the next field. Can it do it on its own? Or do you need to stand next to it just to make sure it's a safe action there? Probably technically it's really easy to do, but it's very hard legally to actually make sure it's safe. Finally, I'm talking about social aspects as well. So a robotic solution might technically be brilliant, but it can still fail if people think it's a non-ethical solution. And a very good example I can give there is that I had a company once asking me to generate an object detection system in front of a combine harvester, and it was driving autonomously. And when it would actually detect small living animals in front of the machine, it would stop driving. And then the company asked me, can you actually make it in such a way that you can ask the machine to take care of the bigger animals, and the smaller animals you can just basically crush because at some point you can't stop for any animal. Well, and then, which animals are we crushing and which we are not? Well, that's ethical, an ethical question right there. So think about that. It's really important. So this is all these questions are identified and helped answering in an ELSA scan. We can do that for you. Then I'd like to talk about user acceptance testing. So we developed a protocol in Wageningen for user acceptance testing. Really important, talking about usability and trust. So if farmers don't trust or understand the machine, they will never use it. And it will basically mean your entire development will fail. Think about how intuitive a solution must be. Can a farmer just start using your machine? Or do you need a very complicated training? Or you even need a training of a week, for example. I also like to mention financial viability, of course, which is a no-brainer. System must be cost-effective, but when will it be cost-effective enough, for example? It has to fit a business model for a farmer as well. And another thing which is really, really important, we found out, is social influence. So imagine a farmer seeing his neighbor actually adopting a new machine, and his neighbor is really enthusiastic about it. Then you can tell that that very farmer will be very eager to adopt himself. So really important, user acceptance testing, really to ensure your technology actually meets the real expectations of an end user. Then our third toolkit is business model validation. And it actually consists of two specific models. The first model has a fancy name. We call that a triple layered business model canvas. And what it does, it's actually extending beyond the classical financials. And we actually look further, actually to capture the full spectrum of value. So then I'm talking about economic, environmental, and actually the social domain. So first, there's the economic layer, first of the three, which is traditional business value. Then there's an environmental layer, all about sustainability and impact, environmental impact. So what's that worth in euros? For example, a CO2 reduction. And there's also a social layer, of course, as I mentioned, societal values. But this is just the first model. The second model is actually called an empathy map. An empathy map helps business really understand the thinking and the decision-making of an end user. So think of a farmer. What we want to discover is actually, what does a farmer say? For example, I want to reduce labor cost, but I still want to maintain efficiency. And what does a farmer do? He's using old farm equipment, but he's actually experimenting with digital tools for example, better yields. What does a farmer think? So will this technology actually work for me? Is it worth the investment? We're also talking about what a farmer feels, excitement about new innovations, but also very worried about costs and complexity. And finally, what does he see? What does he hear? We're talking about influences from peers, from media, from his neighbor, as I mentioned. So other farmers actually sharing a good experience is really, really important to successful implementation of a new solution. The last toolkit is the economic assessment. So it's more of a classic cost-benefit assessment, really enabling stakeholders to actually quantify financial impact on their market of a robotic solution. For example, how many apples does a robot need to pick in order to be financially feasible, for example? How fast should a robot actually be able to weed in a crop? Well, it's a scientific substantiated model. It's all based on the farm accountancy data network. And it actually presents an overview of market implications for you. So all of these tools generate advisory reports that help developers refine their technology. And we really advise everybody to look at this during their investigation and during the development and not at the end, because you might be too late. Because actually, during testing, you're just not only testing robots' performance, you're ensuring that the entire solution is viable from multiple critical perspectives. Our services are already available through the Next-Gen iTech programs and Agrifood TEF, both actually at present on FIRA today. And as a last remark, I want to say, so in Wageningen, we are just not testing if a robot works, but if it fits within real-world farming. Super important. So we are looking at if it's technically fit, economically fit, and socially fit. So if you're developing agri-food technologies and you really want to ensure they create value, I say let's talk. Thank you.
Thank you very much. We have time for one or two short questions. Is there anybody who wants to ask some questions to Jente? Yes, Marco. I'm quite sportive.
Hello, thank you for your presentation. I have a curiosity about the user acceptance models that you adopt.
What was the question about
the user acceptance model you adopted?
Sorry, about user acceptance and then?
Model.
All right. So first of all, we use a survey. So it's a big questionnaire, many questions. So we listen about, we think about what farmers have to say. And then I can actually share some scientific publications about it if you want to. So it's actually the outcome will be a report, and then we say, well, this will be a risk for your development, and this is going well. So we indicate which areas are going well or can actually form an issue for a farmer. So that's so the outcome will be a report. And I hope that answers your question, kind of.
At theoretical level, is there any model that you take
like an AI model
as a reference? Well,
I'm not really sure if it's a peer-reviewed model, but well, at least we are working on that. But yeah, there is a model. There's some way to interpret the results.
Okay.
Yeah.
So it's basically a structured interview guideline that you develop.
Exactly.
Okay.
Yeah, that's true. Yeah.
Thank you.
Thank you very much. And so thanks again to Gente, because the time is going on. So you can keep on talking after during the coffee break and the end of the day. And now we will switch to the last presentations. Unfortunately, our speakers wasn't able to come up to Toulouse, but he has recorded short videos of the talk time, and he will join us by video conference after the videos will be diffused.
Hello everyone, thank you for inviting us to present our work done with Stefan. We are two agroecologists at INRAE based in Dijon, and what we are going to present here is work we did to evaluate what would be the interest to use a robot for avoiding that weed seed produced a given year will contribute to seed burden and contaminate the next seasons. As you know, weed management options are several, but most of the farmers will concentrate at controlling germination and the seedlings by using herbicides or using mechanical weeding early in the seasons. Here we will focus on a way to add a new complementary measure where we want to remove the weed heads before they have shed seed in order to reduce the seed burden the following seasons. And the question is, what would be the gain at using precision farming to do that work? A vocabulary to describe this practice is not fully stabilized, and there are people saying that this is weed surfing, what others will say weed trimmers, toppers, or head clippers. Here are a few examples of machinery able to do that. It is often said that when you look about ryegrass efficiency, those machinery are able to remove about 90%, so they are very efficient. And if you come too late, then the weed seed maturity is already here, and so there is some interest to remove and export what has been clipped out of the field in order to avoid contributing to the further contamination. This practice done by farmers is usually done at 9 up to 12 meters large machinery, and because of the oscillation you have, you need to keep 5 centimeters above the wheat heads if you want to avoid cutting them. And of course, this is where there is some opportunity for trying to catch them with precision. And that's precisely what we intended to measure with an experiment I am going to present. So what the farmer will usually clip easily is what is in orange in that graph. What we would like to catch is what is in blue in that line, that graph, and what is in green is already in the crop canopy, and you can't expect to catch that without injury on the crop. So that's the way we design different layers. The red one, H1, is what the farmer will catch easily with his practices using with surfer. H2 was what we have in those 5 centimeter, and that's what we want to catch using precision. H3 and H4 are within the canopy. The field experiment was done 3 years. We concentrate on 2 weeds, blackgrass and ryegrass. It was done in 3 places in France, and I'm only going to present the results we got on winter wheat plots on blackgrass. The methodology we applied in the field is that for each plot we had 3 replicates. We did that at 3 dates, in May, in early June and mid-June. On each date we had 2 samplings, one where we cut separately the 4 layers and keep them separate, and the other one where we only cut H1, and that's the control of what the farmer would get as a result of using with surfer with a large machinery. At those dates, we also did some measure crop height, minimum and maximum width height, in order to design the good size of the layers. Back to the lab, we did 50 seed samples. Those seed samples were treated with 2 chemicals in order to stop dormancy, and they were put in good condition in growth chambers at 20-25 degrees and 60 hours light. Then the germination were counted over 1 month. This is a technique that the technician in the lab known quite well, and they are able to use that with a large success. So now the results we got. The first one about the density of the infestation. The mean density in the plot was 133 blackgrass per square meter, representing more than 800 spikes per square meter. Each plant had more than 400 seeds, each spike more than about 100 seeds, and that makes an overall contamination of 93,000 seeds produced per square meter. As you see, there was definitely something to do to avoid maintaining such a high level of infestation. Now what we got from the analysis of the different layers is that 40% of the seeds are above the weed trimmer. That's what the farmer will usually catch. And if we target that with precision machinery, we also add the H2, and the overall H2 in addition to H1 will represent 58%, so 60% of the seeds. And this proportion is increasing over time. As you see, this is because the wheat has its maximum height, while the weed, the blackgrass, will continue to grow, so you can catch more of the spikes when you come later. But at the same time, if you come later, the viability of the seeds will become more, will be done, and so you will get more mature seed. The overall viability was remaining quite low, less than 40%. And we see with this experiment that it does not depend on the position within the spike. And those information were interesting to know how the infestation will evolve over time. So we multiplied those 2 figures and we got that synthesis, which shows that if you come too early, you don't catch all the spikes. And if you come too late, there are a lot of viable seeds already produced, and they will go to the weed seed bank. So in the late state, you really have to export out of the field what you have cut. And there are specific machinery able to do that, and this is an example. And it is said to be expensive, but also to be very efficient, allowing to come late in the season. So now with all this information, we wanted to know if there was here something that a robot could do. And we first had a look at the literature about mechanical cutting. Clipping is also the word which is considered for this action. We found rather scarce references, about 38, and they were all very different because the measures were changing according to the timing, to the species, to the number of seasons considered, whether there was another weed control strategy considered at the same time. And what we found is that mechanical cutting is seldom in the title of the article. They are more general. They are referring to management or weed biology, so they are not easy to catch. And usually what they say is that clipping is perceived as a complementary measure to be used when insufficient control makes weed infestation becoming harder to control and manage, and this will be especially the case when herbicide resistant evolution applies in the situation considered. So we have enough to make some projection scenarios, and this will be based on having some parameters you need to decide and fix, such as the speed and life of the machinery if it's done by a robot, what will be the mean weed control improvement, on what is the total duration on which you can apply this strategy, are there time constraints, does that avoid treatment with herbicide, and what were the mean price of those treatments? And is there any capacity to give a monetary value to the weed heads that have been removed if they are exported out of the field? Based on those information, you can produce a depreciation table linking the price of the machinery to the volume of its use. And so we decided that a robot would be able to work around 20 hours a day. The width of his work would be 1 meter. The speed of would be 3 km per hour. And we make a strong hypothesis that about half herbicide treatment would be avoided thanks to the topping measure, which makes that about 2 herbicide treatments can be removed over a 4-year period. And we decided that each treatment would cost a mean 50 euros. So based on those values, if the robot costs 25,000 euros, it may pay for itself if it works on 300 hectares, so representing 50 full days and 2 seasons of work in the favorable period in France. At 50,000 euros, it would take about 3 to 4 seasons to pay for itself, unless you find a way of exploiting what is removed, selling the hair in a methanizer, or having a business model that involves the participation of a third party to purchase the robot. If more expensive than that, it will be very difficult to get your money back using a robot for this application. So the conclusion of our work is that according to the experiment, we saw that there was a large benefit to use precision when cutting with heads. It represents 20% benefit compared to a large machinery. And we also found that the action to be taken is relatively simple to carry out, and that several of the technical logical steps needed to be mastered to do so were already known. So we can probably get a robot to do it. Now, if the reference situation is a case where you can use herbicide, we saw with the calculation that it will be difficult to reach robot profitable stage. At the reverse, if you now consider that already half of the herbicide active substances have been removed from the market, and we expect that we will lose a further half by 2033, then using a robot to help keep the field clean may worth the effort. I would like to thank you for your attention. I would like to thank the team in UMR Agroecologie in Dijon and in the experimental unit. We got the money from 2 projects, and we had interesting discussion within scientific groups, including RobAgri. Thank you for your listening. And if you are interested to continue with that work, please feel free to contact us. We will be very happy to try to contribute to go a bit further in this evaluation. Thank you, everyone. And I'm now ready to answer a question if you have.
So thank you very much, Xavier. I think you can hear us, and you are in direct live from Toulouse, between Toulouse and Paris. So thank you very much for your very clear presentations and very challenging. So maybe we have some questions in the audience. Is there any question for Xavier? Please hold the... No question. While people are thinking, I have, of course, one question, Xavier. So I believe that the requirements you talk about, you have not found any robots today that are able to do such work.
Yeah, that's true, but it could probably be something we could manage rapidly, as I mentioned at the end of my talk. One of the challenge is that if you want a robot to work on a 1 meter wide, you need that it goes into the car. And so wheels are not probably the best strategy. Maybe you have to organize systems such that the robot works and goes and fits in order to go within the car without injury. And so there are adaptations you need to do. But cutting is something which is relatively simple to do, and the robot arm could very well do the job.
And you did not mention the multifunctionality of robotics because you talk about very specialized constraints. Is it something that you have studied also, the multifunctionality of robots?
Well, you're right. Of course, that's a good option, is to imagine that the robot is able to do several actions, and so wheat cutting would be one of them. It's a way of decreasing the costs, and so to have an action done at the moment where the robot is probably not involved in removing the seedlings because it's too late. So that's a way to improve the return, economic return, and so that's a good option to analyze, yeah, sure.
Okay, thank you very much. Is there any question? Very short question? 1 time, 2 times, 3 times? No regrets? So, Xavier, thank you very much for being in distance.